All right. Calculus 2. Give me a second. Let me erase all this. This is from the Cal 1 class, and then we'll get going. Hmm. All righty. We are done with that test. So that test was all about integrals. Basically, how do you do integrals? How do you integrate? And so I was saying that the second half of this class is really about applications of integrals. So that's where we're going to get into. Everything that we're going to look at after this is kind of let's apply integrals and do something with them. One of the first things we're going to do then actually goes back to something we touched on first part of the class when we were kind of learning what the integral is about. And one of the things we talked about is that integrals were about finding the area under a curve, right? That was actually kind of, again, the old problem that Newton and Leibniz were trying to figure out, were trying to solve. They essentially invented the integral to do that. So integrals tell us the area under the curve. So for instance, my function is maybe, to make it really simple, just as a visual, as a demonstration, if my function is something like y equals x squared, then the graph would look roughly like this. And let's say I wanted the area from, I don't know, from maybe -1 all the way to 2. I wanted the area sort of under this curve. Let's just go. I mean, it doesn't matter either way, but let me get, just for simplicity of visual, let's go from 0 to 2. So if I wanted the area here under this curve, and we know we can take the integral of x squared, 0 to 2. So if I want that area, I can take the integral from 0 to 2, x squared dx. That would give me the area under the curve there. All right, so one of our first applications of integrals we've already actually done is the area under the curve. So today we want to look at, and this is section 7.1. Today we want to look at what if I had two curves and I wanted to find the area between them. So for instance, need this to erase quicker. Well, yeah, let's do it this way. So give me a second. Let me draw up one of their examples they have in the book. But I think it'll be better if I draw it rather than project. So this is, and I'll give you the exercise number so you can look at it too as I'm putting this up. So this is number 6, 7.1. And let's see, do I want really matter if I do this? So one of these f of x is gonna be I'll make f of x 2x plus 5, and I'll make g of x squared plus 2x plus 1. And when you graph these, so what I want to show you is, I want you guys to see the graph that you see in the book, if you have that up. But give me a second. 2x plus 5, when you graph that out, we're gonna have here, have a point here, here, even have some points down here. You guys kind of know how this works. You don't have to write all these points, but I will for sake of the future of this problem. So we get a line. This easy enough. First power, we knew it was going to be a line. Then x squared plus 2x plus 1 has a vertex here, point here, and then a point there, and a point here, and a point there, and a point there. Here, and we can draw a parabola through there. Again, the x squared, so you knew it was going to be a parabola. Squared plus 2x plus 1. And notice that, so if I have both these curves on the graph at the same time, naturally there's a bit of area. There's literally a little region between these two curves. So what we want to think about is, how could I go about finding the area between those two curves? And also, just before you even answer that, think about how useful this is. So I'm saying applications of integrals, and I'm sure some of the stuff we're going to look is kind of esoteric. Just kind of doesn't have a ton of uses or is more abstract, but really I want to focus on a lot of, or at least going to focus on a lot of applications to begin with that are really actually like fundamentally useful. So get some shape like this, you would have to, again, if you were machining or milling something, or you were designing something with a 3D printer or something like that, and you wanted a piece of plastic with this shape, you would have to plot this line, and you'd have to plot that line, and then you'd have to, let's say you wanted to paint over that piece of plastic, you'd have to know that the area between there. Again, for yourself, maybe not. You're just a hobbyist, whatever. You just pull out some paint and you do it. But if you're a manufacturing plant, you need not only efficiency, but you need to lower your costs. You need to know exactly how much paint you're going to need, so that when you do this, you're not buying too much paint and then wasting a ton of money, right? So you really need to know how much exactly is there, so that you buy enough paint with maybe 2%, 3% air or something like that. You're gonna have little bits of paint that get everywhere else, etc. But you really actually need that. It makes your process more efficient, saves you money, lowers the cost to you, which hopefully lowers the cost to the consumer, right? So anyway, so this is actually ridiculously actually practical. How do we find, so the question is, how do you think you'd find the area between the two? Give me a second, I won't pause, but give you guys a second to come up with some thoughts. And so it ends up, so if we think about this, if you go back to, so you probably guessed exactly what this is. If you go back to geometry class, saw back to a geometry class, I always tell people geometry, there's certain strategies in geometry to get to a lot of the more, I won't say complex, but just the problems, those problems they always gave you where you had to combine figures or like get the area of some odd shape. And there was pretty much one of two approaches. Like when you got those types of problems, and it's not just area, by the way. So in a lot of geometry, you have two sticks you're putting together, right? You have two objects you're putting together. You have, just there's a lot of problems like this that are not just about area. Um, but area, volume, length, you get a lot of these problems um, where one of two strategies, pretty much like literally, there was two strategies that got you these problems. You either found the area of two things, in the case of area, found the area of the two shapes individually, and you stuck them together, which means you added, or you found the area, like there was those problems where it'd be like a circle with some shape taken out, right? So you'd find the area of the circle, you would subtract out the area of the inside shape, or the other shape. Um, so you essentially, in both those strategies, you're finding two areas. If you're conglomerating them together, you add them. If you're pulling one out, you subtract, right? So two basic strategies that gets you a ton of problem. So it ends up, this is just your geometry class over again. To get the area of this little part here. So what we're trying to find is the area here. One way to think about this is if I didn't have the parabola, I could find the area under the straight line, right? So this area is just the area under the straight line minus the area under the parabola. The area that you have kind of under the parabola from the other thing about this problem, one of the nice things about having the graph is you can see naturally where these intersect. So you can see this intersects at -2. You can see this intersects at +2. It's supposed to be, at least it is, but so this area is literally the area under under the straight line minus the area under parabola. That's it. So if I set up an integral so if I took the integral from -2 to 2 of straight line minus the parabola, then that would be the area under the straight line minus the area under the parabola. There you go. You have the area between the curves. And honestly, that's it. That's today. That's kind of the punchline to the joke. If you want the area between two curves, first you're going to need a picture of what's going on, so you sort of know which curve is the correct one to start with and subtract, and which one to subtract. But you just take the area under one curve and you subtract the area under the other curve. It's just old school geometry. It's basic geometry. So again, what I'm saying here is the area here. So again, from the picture, I see sort of the natural, like where these two graphs intersect. So I see the natural boundaries here. Boundaries start at -2 on the left and go to 2 on the right. So what I'm going to do is I'm going to take the integral 2x plus 5. Second. Say it right here. And I'm going to subtract x squared plus 2x plus 1, all this dx. So 1, some bigger set of parentheses around that. But again, this is, so 2x plus 5 dx from -2 to 2 gives you the area under the line. Then you're subtracting the x squared plus 2x plus 1 dx gives you the area under the curve. You just take the bigger one, subtract the smaller one. Bingo, you got it. So that's it, actually. Honestly, is this whole section. So notice from here, not only is this, so first you have some subtraction to do here, so you have some easy algebra, but then the rest of this is exactly what you guys just did for the first half of the class. So that's the other thing you're going to see about a lot, not just this application. So that's the thing you're going to see about this section. I'm not introducing any new integrals or techniques for integrals or any of that. You actually already know mathematically how to do every single thing that you're seeing here. It's really just honestly getting the picture set up so you can You know how to set up this integral, essentially. You know which one you're starting with and which one you're subtracting. But after that, it's just algebra you already know, and now integration you already know. So it's easy. So you're gonna keep seeing that. So not just this section, none of the stuff we're doing um that like introduces any new integration techniques, any new styles, any new strategies. We're actually not gonna learn a single bit new things about integration. We're just going to apply integration. So if you see an integral in this, as long as well the what do you call it, as long as I set up the problem right, it's but I mean if you see an integral in this, what I'm saying is it's an integral you can do. So let's see if you can work this through. Go ahead and pause on your side, I'll pause on my side. Go ahead and work that through. All right, let's see what we get here. First of all, subtracting these, let's see, the nice thing here, two x's cancel. So we get negative x squared, 5 plus 1 is a 4, so plus 4, that's all be dx. And then we had to integrate from there. So negative x squared, that goes up to 3, divide by 3. So you're gonna end up with negative 1/3 x cubed plus 4x. And we're gonna evaluate this from 2, negative 2. Getting all right, and this then is gonna be 2 cubed is 8, 2 is 8, so we end up with first part is 8 minus 8/3, and subtract -2 when you cube it. Wow, it's gonna be a lot of negatives, that'll be fun. All right, so we're subtracting. -2 cubed is -8. -8 times this is a positive 8/3, but then we're still gonna subtract, so minus another 8/3. Then -2 makes that -8, minus that is plus another 8, so we actually get, interesting. This function is symmetric, so that doesn't make sense. So we're gonna end up with 16 minus 16/3, which is 32/3. That'll be 48/3. So the area between those two is 32/3 square, whatever units we're working with. Meters, centimeters, inches, doesn't matter. That would be the area between the curves. Like I said, look, that's it for all these problems actually. So let's work a couple more problems just to highlight. I think I'll try to highlight, especially problems where you need to set up the picture yourself, but just try to highlight a couple things in these problems, and then that'll be it for this section. So let me find the next problem. All right, so I think let's do one more where they included it. So this will be another one that they included a graph for you, but I'm gonna recreate it on the board anyways. So this is number 10. And then we'll get into some where you have to create the picture yourself. So you'll see in the homework, that's actually one of the big skills they actually test in the homework. Is not just the integral, but actually you creating those graphs yourself. But let's say x, it's x minus 1 cubed, and g of x, I think x minus 1. So the graph of this. Let's see. So x minus one, when you graph it, is going to be like this. Something like that, right? X minus one cubed. X minus one cubed has an x-intercept here. So it's an x cubed graph, move to the right one. So again, when we get to these problems, you have to graph it yourself. And since you aren't allowed the graphing calculator, again, what we're testing is, can you sketch these graphs? So not looking for exact, but can you sketch these graphs? Do you know what the shapes of the graphs look like? And do you know what the transformations, can you see the transformations on the graphs? So, for y'all and Cal 2, I think this will be easy enough for you guys. A cubic graph looks like an S. This is move to the right one. So you do a couple of calculations. What you're going to see is you're going to have a point here, here, and here, but the cubic graph looks like this. It's going to look roughly like that. And I actually should have drawn this so I could have sized in, but the idea is, again, essentially, so if I want the area between the curves, notice that this time there's kind of two parts to this, both these little parts. Now, in coming up with this integral, so let's kind of talk about writing the integral, because there's a couple points I want to make. There's also, this is one of these, there's not a certain way you have to do this. You just have to, as you're putting it together, you have to be aware of what you're seeing visually and how the integral lines up with that and what that's going to do for you. But again, notice that unlike the last one was nice in that there's sort of a left end and a right end. And notice that the 2x plus 5 graph on the last one always stays above the x squared plus 2x plus 1. Here with x minus 1 cubed and x minus 1, there is one half of this where the x minus 1 cubed is above the x minus 1 graph. There's another half of this where the x minus 1 is above the x minus 1 cubed. So we still want to write an integral that gets the area. So one way to do this is to treat each of these little portions naturally. I think it's natural to just treat them separate. So you have one portion from 0 to 1, so an integral from 0 to 1, where the x minus 1 cubed is above the x minus 1. So don't even have to pause for it, but then how would you write, so for this first half, this first portion, how would you write the integral there? So that would be x minus 1 cubed, since that's on top, minus x minus 1. This is all dx. So that would give you not the area of the whole region, but just this first part from 0 to 1. And then we have a second half from 1 to 2. Then basically what we could do is we could add, go from 1 to 2, but in the second half, the x minus 1 is on top. The second half would be x minus 1 minus x minus 1 cubed. And this is good. So you work this through, this is going to get you the answer. But one thing I do want to mention, and you're not going to see this in every, so part of the reason I wanted to write it out this way is there are going to be some graphs where you kind of have to do this because they don't have the symmetry that this graph does. So I wanted to write it out this way because at the least, this is always going to do it for you. Identify each portion. And going back to, like I said, one of the strategies from geometry, if I have two shapes and I want the area of both of them together, then I add the two, right? So this will give me the area of the first little eyelid or whatever you want to call that. first little shape there. This will give me the 1 to 2 will give me the area of the second. I add them together and I am good. However, notice that in particular, so just this, the functions they chose and the way this plays out on the graph, there's, the x minus 1 cubed has symmetry around this center point, and then so does a line. A line has symmetry around any center point. So it ends up, I mean, we can sort of confirm visually, but also with the symmetry that we know these two shapes have from looking at them in geometry and algebra. That so basically you can kind of see and that the area of these two parts is exactly the same. So if you know that they're the same, if symmetry tells you that these have to be the same, then instead of doing both of these, I basically could just do 2 times this. So another way to do this is I could just do 2 times the integral from 0 to 1, x minus 1 cubed minus x minus 1. Because again, symmetry just tells me these are going to match anyways. So why do the work twice when you can do it once and multiply by 2? Now, as long as you know that it has symmetry from what you know from college algebra, then yes, go ahead and do this. Why do this twice when you can do it once and double it? What I'm saying is there are definitely going to be some other problems where you don't have symmetry between these two pieces. Then you really are going to have to do the full go. You're going to have to create both parts. But in our case, we can get away with just doubling this. So that's what we want to do. So let me have you work through that. Pause on your side, I'll pause on my side. Go ahead and see your way through this. All right, let's see what you got here. Now, so one comment I want to make, or maybe a question, you guys. So how many of you guys went ahead and actually multiplied x minus 1 cubed out, subtracted the x minus 1, kind of combined like terms, did all that? It'd be actually interesting if I could hear you guys' responses, because I think this is usually kind of about a half and half thing. I think a lot of people would look at this and go ahead and do that. And I'm saying that's, I think, what you've seen in algebra, kind of the correct go, right? So you do x minus 1 times x minus 1, and then you do that times x minus 1 again, and you subtract x minus 1, and it takes you a while, but it does the job and it gets the work done, right? So what I'm saying is that it's completely legitimate, works fine. However, now that I kind of have the chain rule basically from derivatives, I'm going to save myself some time. So what I'm saying is that if you did that, that works fine. And it's like, yeah, it works fine. There's nothing wrong about doing that. However, I know that that's going to take a long time. And so what I'm going to do instead is I'm thinking of this in terms of, or this part in particular, this x minus 1 cubed in terms of chain rule. This is an x minus 1 plugged into basically an x cubed, a power function. So I can take advantage of that. Instead of having to multiply everything out and combine like terms, I can take the integral of this using, sorry, I was saying chain rule, which is true. But I can take the integral of this using substitution instead. And that'll just save me some time. So, especially because the substitution here is that u equals x minus 1. The derivative of u then is dx, so it almost doesn't even really change anything here. So I'm going to treat this as a power function. I'm just going to divide by the derivative of x minus 1, but the derivative of x minus 1 is 1, which doesn't change anything. So this is going to end up, this part is going to end up being, so we're going to have 2 times. This part's going to end up being 4th power divided by 4, so x minus 1 4th power divided by 4. Now this part could actually do that same substitution, but I also can just I can distribute the negative and just do this for real. So minus x squared over 2, it's plus 1, so plus x. I'm going to evaluate all this from 0 to 1. I love it when I get 0. By the way, that's why I would also choose this particular integral over this. So we could have also doubled this integral if you wanted to. This one allows me to plug in a zero. I like doing less work and easier work when I can. That's called laziness, but it's also called efficiency. Two sides of the same coin. So use it to your advantage. Use the laziness to give in to your hate. So this is beautiful. I'm gonna plug the one in all the way through, but the zero, when I plug that in, all of these are gonna turn to zero. So I only really need to plug in the one. So this is gonna be 2 times, and 1 minus 1 is 0, so that goes away. 2 times -1/2 plus 1. Very nice. Okay. Um, that is 1/2. 2 times 1/2 is a big old 1. So the area of this is 1. Yeah, 1 square unit of whatever your paint is. All right. And these were nice because they, at least in the book, when you see this problem, they provide picture for you. Let's look at a couple problems where you have to build the picture yourself. So let me. Yeah, that's what I was trying to do. Go back up. All right. I think actually what I'm gonna do is sort of create my own on this. So they have some decent exercises in the section, but they're sort of not that great. They're repetitive. So but I'll create some very much like what you're gonna see in the section. So, so on this one, let's do, um, so same thing, find the area between the curves. This time, let's do, um, one of these, the cube root, x minus 2. what I mean. Two. Those magnets. Let's change this to cube root of x minus 1. Helps. I think that's 1/2 squared is 1. Works. There. Something like this. Okay, sorry, just it's debating kind of what I wanted this problem to be, but I think this is good. So we want to, kind of like I was emphasizing in the last one, you want to graph this out, and from the graph, you should see your intersections and stuff like that. I do want to make the comment that sometimes the way they give you these functions are just basically, sometimes from graphing it out, you're not gonna be able to see the intersections, and that's when you actually gotta basically find the intersections. And you guys have already done that in an algebra class before. You essentially just set the two equations equal to each other and solve, and depending on what the equations are, you get sort of different type of solving. Literally could be solving quadratic, a polynomial, a rational function, etc. But you guys know the techniques for that. So in this case, I do want to focus on a problem where you can graph it and then see those intersections from that. So that is, but yeah, sorry. So purpose of not, like I said, this problem and at least one or two more that we'll look at is your job to graph it so that you can see these areas. So this is actually what I want you guys to practice, to kind of practice with. So I talked about it a little bit on the last one, just recognizing what type of function it was and therefore what shape. Then go ahead and get the graphing going. So I actually want to have you guys pause and I'll pause. I want to see if you can get the graphs of these two going again without a calculator. See if you guys can do that. And I was thinking too, I mean, if you had a class, if you had a college algebra class where they just kind of let you use a calculator to get all these graphs, you are going to be at a disadvantage here. But nonetheless, we can work through that. So for the first thing is, so I'm thinking about the cube root graph, and the cube root graph, what does a cube root look like? A cube root actually looks like a cubed, but instead it's kind of flipped over its side. So a cube root graph normally looks like this. And then what's the transformation that's been done on this graph? It's been moved to the right one. I can draw that out pretty easily. Roughly make these larger this time so we much more of the visual. Right, so this means our center point is gonna now be at 1, 0 instead. And it will come out this way. And it'll go up this way, and then it would, so our graph is gonna look roughly like this. Probably actually a little more curved out, not as steep as I made it there, but roughly something like that. X squared minus 1. So what is an x squared? What shape is that going to give you? Good, that's a parabola. Where is the, again, so let's read the transformations. What does this minus 1 do to it? That's going to be down 1. What does this 1/2 do to it? Remember that multiplying stretches the graph, either stretches or compresses it. In this case, because it's 1/2 outside of the x squared, that's going to be a vertical compression. This one, that's a parabola that's been moved down 1. Then that means normally what it would do, so I sort of have the patterns for x squareds memorized because I've done it so many times. Normally what it does is you go over 1 and up 1, and then over 1 and up 3. It's going to be then over 1 and up 1/2, over 1 and up, basically up to here. That's sort of, yeah, the way I designed this when I was coming up with the function. Like that, something like this. So this parabola looks like this. And we get a nice little and kind of eyelid, teardrop, something like that area there. And again, once you have it, then you can read off your integral. It's like, just like we did for the past couple of problems. So once you have it, it's clear that my intercepts, two graphs intersect each other at x equals 0 and x equals 2. So I can build my integral from 0 to 2. And then I'm going to do the top curve minus the bottom curve dx. What's the top curve in this case? Good, that's the cube root of x minus 1. What's the bottom curve? Good, that's that 1/2 x squared minus 1. All of this dx. We can go to town on that. So let me have you do that. Let me have you finish out the integral there and let's see what the area is. Go ahead and pause on your side. I'll pause on my side. Sweet. Okay. So and you'll see kind of honestly a bit like the last one. I'm gonna use substitutions, quote unquote, to integrate that part. This part is just simple power functions. So this is gonna be, so this is really x minus 1 to the 1/3 power. That'll bump up to 4/3 and then divide by that. So it'll be 3/4 x minus 1 to the 4/3 power divided by 1, which doesn't change anything. Then we have minus the 1/2 x squared, so that'll be up to a 1/3 power divided by 3. So now minus 1/6 x cubed plus 1, so plus x. All of this evaluated from 0 to 2. We can go to town on that. Again, got very nice fortune here that the 0 plugs in and everything's a 0. So I'm really just plugging in the 2. What I see there is 2 minus 1 is 1. 1 to the 4/3 power is 1. So that's going to be 3/4. 2 cubed is 8. This is actually going to be 4/3. 6, which reduces to 4/3. And then plus 2. And let's see, common denominator is 12. That's going to be 9/12 minus, what is that? 16/12 plus 24/12. 3 minus 16 is, what I see here is 17/12. So the area of this is 17/12. All right. And then some other problems you might see, they'll give you maybe two functions, but they'll also give you some, basically, they'll give you the boundaries they want you to integrate it in. So we've seen several problems in a row where basically the boundaries were your intersections. But that's not always the case, or just not always what we're gonna look at. So let me show you an example. Erase this and then put up an example for you. So we're gonna look at 19, but I'm gonna alter it just so the visual is a bit easier. So they're gonna give you like the following. So instead of, it says 1/9 x². Let's see. Let's do something like 1/2 x². So the function is 1/2 x², but then they give you these other, so notice the rest of the boundaries they're given there, I'm gonna keep the same. So instead of giving you another function, they say y equals 1, x equals 1, x equals 2. That's fine enough. So the thing with this is like, okay, like don't let something like that fake you out. Still your first job, I mean, basically still just draw. Your first job is to draw what's going on. As I sort of know already in my head, like this is a rational function. But I'm dividing by 2x². So whatever I plug into x, I'm gonna get a pretty large number on the bottom. So I already know this is more of a scaling thing that I'm thinking in my mind. When I graph this out, I'll maybe do 1 there, maybe 2 there at best. I'm not gonna do a lot of pieces there. So let's do 1 here, there. Well, then we can sort of do similar 1, 2, -1, sure. But when I graph this out, so this is going to be a rational function where you have vertical asymptote right at x equals 0. That's what makes the bottom of this fraction 0. So we have a vertical asymptote already here. And the horizontal asymptote technically y equals 0. So I know that the way this works is one of these graphs is going to be like this and one of them is going to be like this, or vice versa. When you plug in positive numbers here, you're gonna get a positive here. So this side is gonna come down like this. So like for instance, if you plug in, well, you plug in a 1, this is gonna give you 1/2. You plug in a 2, it's gonna give you 2 squared, which is 4 times 2 is 8, so that's a 1/8, which is a lot lower. And it would keep going down towards the x-axis there. Then if you plugged in sufficient numbers here, you basically would get kind of some similar things. If you plugged in a half, they would be going up. So if you plugged in a half here, a half squared is 1/4, times 1/4 is 1/2. Flip that over, you get 2. So 1/2 will give you 2, and it will kind of keep going up like this. So this curve goes something like this. Goes really hard at the x-axis. Never touches it. Kind of similar here. Goes hard at the y-axis, but never touches it. Now let's add in these extra pieces here. So it says y equals 1. So y equals 1, what type of line is that? What would that look like? Y equals is a horizontal line, so we have a horizontal line, and I'm going to put this one dotted here. And then we have x equals 1. What type of line is that? Where would that go? So these are vertical lines. So we have vertical line at x equals 1. Vertical line at x equals. Now the fun thing, the tricky thing about this is, so then what, these lines intersect and create a bunch of different little quadrants and, areas. They create a bunch of little spaces between the lines. Which one are they asking for? What are we actually, they're asking you to find the area between this curve and all of this. Where is that? So the slightly tricky thing about this one, I would say the fun thing, but the slightly tricky thing is, so remember, so I started off by saying they did give you 2 functions, but technically they did. This y equals 1 is your other function. So the idea is you need the space between y equals 1, between 1 over 2x squared, between x equals 1 and x equals 2. So y equals 1 is actually your top here. 1 over 2x squared is your bottom. X equals 1 is your left. X equals 2 is your right. So they want this area right here. That's the area they're trying to find. And if that's the area we're trying to find, then that means my integral. So that I would say once you have this, once you figure out which portion of that picture you're really looking for, then honestly, even without the picture, once you have the picture, then that completely tells you you have everything you need here to build your integral. It tells you everything you need there. So again, now I'm not looking at intersections, but I'm still know that I'm integrating from 1 to 2 because that's the left end and the right end of my area that I'm trying to find the area. And then top to bottom, I'm getting the area from y equals 1 down to 1 over 2x squared. So it's going to be 1 minus 1 over 2x squared dx. So top minus bottom from left to right. But then once you have that, you have your integral, and that's easy to put together. And that's kind of easy to do. So go ahead and pause on your side. I'll pause on my side. Go ahead and run this through. Sweet, easy enough. So this one didn't have to do really much of anything fancy as far as the integration. The integral of 1 is x. So we're going to end up with x. And then this is 1/2 x to the -2. So the power goes up 1 to -1. You divide by -1. And so it's going to be plus 1/2 x to the -1. Or you could just write it as 1 over 2x. Oh my goodness, I messed that up. You're going to evaluate that from 1 to 2. That'll work quite well for us. So you plug in the 2. That's 2 plus 1/2, or no, 1/4, I'm sorry. And you're going to subtract what you get when you plug in the 1. So I'm going to subtract 1 and then subtract 1/2. So what that's 1 minus a quarter, basically. So all of this is gonna give you 3/4. So the area between the area in this region here is 3/4. That'll be your answer. All right, let's look at one more. Yeah, I'll kind of look at one more and you'll see why. But one more like this. So this one is going to be 27. This one, I don't think I need to make any changes. So let me just leave the camera, but other than that, I don't change them. Here, your f of x and over x. And then the other limiters here are x equals 0, y equals 2, and y equals 10. So like I said, we're set up very similar to the last problem. All right, so then what I'd like you to do first is get a graph of this going. So go ahead and pause on your side, I'll pause on my side. Go ahead and get that graph in that region kind of fine. All right, so 10 over x. Our graph. Kind of a fun one. So again, it's going to be vertical asymptotes along y-axis, horizontal asymptote along the x-axis. But also they say x equals 0 is one of our boundaries, right? So um, um, x equals 0 is also one of our boundaries that they give to us. 10 over x. Well, so this one's interesting because we also have these other two boundaries are y equals 2 and y equals 10. I actually want to make sure I can kind of cover those first. So that's 1, 2, 3, 5, 6, 7, 8, 9, 10. And those are y equals. So those are actually horizontal lines. First thing about this one to realize kind of is that y equals 2 and y equals 10 are horizontal lines this time. Y equals 2, y equals 10. And then I'm going to be, so then basically what I'm going to do is I'm going to graph 10 over x within those boundaries. So for instance, well, and I'll just not try to leave. There's too much on this. So 10 over 1 is a 10, so we got a point there. And 10 over 2 is a 5, so 2 gets you up here. And 10 over 3 is like 3 1/3. That gets you something like this. And over 4 is 5/2, 2 1/2, etc. And over 5 is 2, so that's where it sort of hits this boundary. And then it would keep going down from there. So this graph is like this, then dips down and it will keep going down towards the x-axis. So then the question is which area on this graph with all these different dotted lines and boundaries are we talking about? So they were saying between x equals 0, y equals 2, y equals 10. So they're really talking about this area here. Up to now the y-axis. Yeah, from here to here. Uh, so now that you got this, what would you guys, well, I won't be able to get your feedback much, but what would you say, or what's maybe different about this compared to not just the previous example, but really kind of all of our examples? So on all our examples, our top and bottom boundaries were basically the function and some other function, or like at worst, like the last one where it was a horizontal line in the function. And our left and right were just, I mean, on the last one, they were vertical lines, but our left and right were just x values, right? They were just the x values that you went from left to right. Notice here that your left to right isn't solely defined. Like your left is defined, but your right is actually defined by the function as you go. So in some sense, it's almost like again, on the last problem, it was a horizontal line and function like we would be looking at it between here and there, like top to bottom. So it's almost like the left and the right here are really what the top and the bottom have been on our previous problems. And notice that your top and bottom here are not functions, they're really just numbers, right? So it's from 2 to 10. So in some sense, what they've done here is they've reversed the role. Your top to bottom is actually kind of like your left to right, whereas your left to right is kind of like your top to bottom. That's what you'd be integrating, what you'd be subtracting. These are really what you're integrating, or like what you'd normally be integrating from to, and this would be what you're subtracting. All right. So because of that, it ends up on something like this, that basically we want to integrate. So we've been used to, actually every problem we've done is we've been integrating along x, but it is possible to integrate along y. If your function, the independent variable is of your function is y instead of x. So if your function says instead of y equals blah 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 x, if it says x equals blah 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 y, then that means the x value depends on the y value. The x value is calculated by the y value, but that means that then your direction that you're going especially when you integrate with the function, instead of going along the x-axis, you're going along the y-axis. So basically what I'm trying to say is we could reconfigure this function so that it's x equals blah 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 y. It's y is your independent variable. Then we can integrate up. We could integrate from low to high and get the area between this curve and just the y-axis. So if you haven't seen it before, basically you can describe functions in terms of y instead of x. So we can integrate along y. I guess what I'm trying to say is we can integrate along the y instead of the x. So really quickly, this function that is y equals 10 over x. I could just resolve this for x, so I can multiply by x and then divide by y. I would end up with x equals 10 over y. Most functions, you can't just switch those places. You would end up with something very different. But they very intentionally give you a very nice function here. So we didn't have to actually touch little algebra there. Just didn't have to do a lot of work. So basically what I'm going to do is I'm going to integrate along y here instead of x. This will be my function now. One way you want to think about it is 10 over x describes this function if you're sort of looking down towards the x-axis or in terms of x. 10 over y describes this function if you're looking towards the y-axis, sort of in terms of y. Now if I'm looking towards the y-axis, my top and my bottom is the 10 over x, 10 over y is my top, but then the y-axis is going to be my bottom. which is 0. So, yeah, let me just, so I can take the integral now of 10 over y dy. I can do this and then from 2 to 10. 2 to 10. And this will give me the area because it'll give me rectangles. So this just goes back to what integration means. It gives me rectangles underneath this curve, but going now towards the y-axis. So it'll give me all the rectangles, add them all up as I go along from 2 to 10. I wanted to show you this because occasionally regions, the way they're defined, it's really basically it's naturally defined, or you can, yeah, it's naturally defined read along the y-axis instead of the x-axis. So turn your function into a function of y and integrate using your y value boundaries there. And really quick, so integrating this would be 10 natural log of y, and I'm going to evaluate that from 2 to 10. And that equals 10 natural log of 10, well, 10 natural log of 10 minus natural log of 2. But we know with logarithms, if there's a subtraction between them, I can combine it into 1 and just divide the parts. So you end up with 10 natural log of 5, 10 divided by 2, and that is the area. This region here. And honestly, that'll kind of cover all the configurations that you guys are going to see. So you're either going to see problems where they just give you two functions where the assumption is, what do you call it? The assumption is they intersect. And so get your graph going, find the left and the right end and do your integral from there. Or they're going to give you problems where they give you a function and several like horizontal and vertical lines as boundaries. But again, graph, find your area that you're trying to find the region that they're describing. And then same thing, integrate from left to right. You should also see, you could easily have a problem where you have two functions and then maybe a left and a right boundary, kind of like 19, but instead of y equals 1, you have some other, not just a horizontal line, but some other substantial function there. But it would work the same way. You would graph it, you'd find the region to be between the two functions, between the two vertical lines, and you would integrate from left to right, top function minus bottom function. It's good stuff. So easy stuff. Area between curves is just integration, some really basic geometry technique. All right. So the next thing, well, I'll see you guys for the next one. I don't want to give out the secret, but we'll look at another application of these integrals. See you next time.